There are only three possible orders for these equations. Okay, there's a zero order, there's a first order, and there's a second order. Those are in AP Chem, those are your only three options. It has to be a 0, a 1, or a 2. In real life, if you Google this stuff, that's not true, but like in AP Chem Funland, this is all there is. Okay, so the graphs of this thing, if we looked at concentration versus time, if it's zero order, it's actually a straight line heading downward. And the question is like, why? Like, why straight line heading downward? So what do you know about the slope of this line here, and the slope here, and the slope here?
It's the same.
It's the same. Because that's the definition of a straight line. It always has the same slope. So if you look up here, and if I wrote slope instead of rate, and with my laggy pen there, so slope instead of rate, the slope is equal to a constant, K. It never changes. That slope is always the same. So I could write that as K times the concentration of my material, which they're calling material A. They could have called it anything, but they said A, raised to the 0 power, right? Because anything raised to the 0 power is 1, so it just disappears. And so for a 0 order reaction, the concentration of the material doesn't matter at all. You get the same rate no matter what. Okay, so if we did my like dating analogy, like it doesn't matter how many eligible like females there are, men are going to get married at exactly the same rate no matter what. If there's one person available or millions, like men are getting married at the same rate. That would mean 0 order, like their concentration does not matter at all. Which is weird. It doesn't happen very often. The place that you're going to see it happen most is radioactivity. So if you are a radioactive nucleus, you're just like, oh, I don't feel good, I don't feel good, explode. But that is totally separate from whether the like nucleus next to you feels like it's going to explode or not. Like it's a totally internal thing. Like if you're radioactive, when it's your time to explode, you just explode, whether your neighbors are doing it or not. You just go. So like if we're putting in terms of this equation, your neighbors would be like A, and they don't matter. It's just you. That's it. Okay, now what do you notice about this slope over here in the first order equation? Oops, come on. You're not noticing anything, are you?
Nope.
Okay, why not? You should be noticing some things. Okay.
The slope decreases.
The slope is really steep here, right? It's steep. Oops. And down here, it's not. It's kind of shallow. So we'll call that shallow. Oops. Okay. So like Katie said, the slope is decreasing, which means that your speed, your slope, is higher when you have a high concentration. So when your concentration is high, your slope is high. And when your concentration is low, your slope is low. Good, not good?
Good.
That's good. Okay. So in a first order reaction, your the speed at which it goes depends on your neighbors directly. Like, shoot, like, should I get married? All my friends are getting married. Like, oh no, like I should get married. My friends are getting married. Boom. So your neighbors are influencing you somehow. And in this case, as more and more of your friends get married, like you have fewer and fewer constant, like the concentration of your single friends is going down. So then if you hardly have any single friends left, the concentration is really low, then you're not going to any weddings because nobody's getting married. But when you're young and like all your friends are single, like people are getting married a lot.
Got it.
Got it? Okay. Now, this one looks the same. When your concentration is high, your slope is high. And when your concentration is low, your slope is low. So you're like, wait, isn't that the same thing? But
It's faster.
yeah, it's a little faster. And again, like if all you have is a curve, you're not going to be able to eyeball it and say, oh, that's definitely first order or that's definitely second order. You can't tell. All you can say is it is not first order. That's all you can say. There's no way to tell by the naked eye whether that's first or second order, just by the curve. Okay, so let me share something else. Hold on, new share. Let's go here. Oops. Gotta change my select button. Maybe I don't have to change my select button. Let's do this one. Okay, that's not what I want to share.
I mean, you showed the ballots.
Okay. I want to share this. So you can see this. It's Mathway's website. Yes or no?
Yes, everyone has used this format before.
Good. I was hoping you would say that. So if I say that my slope, this dx dy thing, is equal to x squared. So I'm saying that my slope is equal to a second order. You follow what I'm doing here? So rate is a slope, and that's got to be equal to itself squared. That is called a differential equation, and you need some calculus to solve it. So that's why I went to Mathway, and I said, like, I can't do calculus. Like, you tell me. And Mathway says, well, wait a minute. There is a solution. One is that, like, you can't have any concentrations. And the other one is that there's this weird inverse relationship. Okay, so you don't need to know any calculus, but I need you to know that if you did some calculus, you would find a weird inverse relationship for a second order equation. If I did the same thing, but just put in like my slope is equal to itself, there's a solution for that, which is that it's nothing. Okay, but if I were to like log in, I would also see that there's another solution for this. Katie, have you done any differential equations? Do you know the solution for this thing where your slope is equal to yourself?
Nope.
There's one curve where the slope of the curve is equal to its value, and that is E, like the function E.
Mhm.
So what we're going to see here when I reshare myself, new share, come back, let's see. Here's my thing here. Okay, so when we look, if we did a first order where my slope is equal to myself, I told you there were a couple different ways to look at rate laws. There were differential ones. And if you did some calculus, you could look at this E as a solution. Now, when we integrate that thing and turn it around, we actually get a natural log equation. So there's another, like, I'm trying to figure out how to describe these things other than you're just going to memorize it. But basically, this curve is described by this equation if we were to graph a natural log. So in other words, if I were, instead of graphing concentration against time, if I did the natural log of concentration versus time, I would get a straight line. So you remember last year in physics where we would like play around with equations and try and figure out what could I graph to get a straight line? This is what you would graph, natural logs. If you were to take this graph and try and straighten it out, you're going to get this weird inverse relationship again. So if you graphed 1 over the concentration, you would get a straight line. So on your chemistry equation sheets, you have 2 equations. This one comes first, the natural log one comes first, and it's easy to remember because that is your first order equation. And this equation comes second, and it is your second order equation. So the key is to get a straight line out of those things. And you'll notice that this K, this like weird constant, is always equal to the slope, right? Slope equals K, slope equals K, slope equals K. But I kind of just lied. Why did I lie? Where did I lie? Does slope equal
The
K?
signs of them?
The sign.
Slope is equal to negative K.
Here's the thing. Chemists have made a definition, okay? And that definition, I'm going to write down, rates are always positive. Always positive. It makes no sense in a chemistry class to say that you have a negative rate. Like that just doesn't, that it's kind of meaningless. Where in physics you would say, oh, well, I have a velocity, my negative, I'm going in the backward direction. In chem, that just doesn't have a meaning. So in order to always get a positive rate, so rate equals K times some concentration. If my slope is negative, they just want you to make it positive. Like whether your slope is negative or positive does not matter. Your answer is always positive. Does that make sense?
Yep.
Okay, so like you have to memorize this because this shows up on so many FRQs. They will ask you, what is the K for this reaction? And you're gonna be like, how do you solve? Well, you find the slope. Slope is K, but it's always positive. Whether your slope is negative or positive, your answer for K, always positive. Always, always, always. Okay, the other thing I need to point out here is that, so we've got 0 order, first order, and second order. And I said, well, wait a minute, this is your first equation on your equation sheet, and this is your second equation on your equation sheet. Where's this equation on your equation sheet? It doesn't exist, and here's why. This axis here is your concentration. So that's concentration of A. And this is time axis down here. If we were in math class, what's the equation of this straight line?
Y is equal to mx plus b.
Y equals mx plus b. But we don't have a y axis. What do we have?
Concentration axis.
Concentration axis. A equals m times our x-axis is time, plus our y-intercept, which is our beginning concentration. Bing, come on, machine. No, don't lag on me. Okay, so that equation is this equation. They're the same thing. So they expect you, like, they're saying, like, look, this is 9th grade math, and you're in AP chemistry. So you should be able to figure out the slope of a straight line. That's why they don't give you this equation. It's not on your equation sheet. Sound good?
Yep.
Okay. Well, very last thing, and then we're going to stop recording. This part of the relationship shows you, like mathematically, if we were to look at concentrations, so if I doubled my concentration or if I tripled my concentration, what happens to your slope? What happens to your rate?
Stays the same.
It's the same, because in a 0 order relationship, the concentration doesn't matter. What your neighbors are doing, no effect. Like, okay, here, this is first order. If I double my concentration, what happens to my rate?
Increases.
By how much?
Same amount.
Same amount, right? It doubles. So if I double my concentration, oops, that's pink. So here's what I'm going to do on lots of data tables. If I double my concentration, so if that goes 2 times and this goes 2 times, that is first order because your rate is equal to K times A times some power we don't know. But if my rate doubled, if this was 2 times, forget your constant for a second, and my concentration did something weird, what power could I put in here to make both sides of this equation equal to each other?
1.
1. Yeah, 2x equals 2x to the first. So that is a first order reaction. Here, if I go up, if I double my concentration, my rate goes up 4 times. So if we do rate equals A again, like this. So if my rate goes up by 4 and my concentration went up by 2 to some power.
2 power 2.
So it's a power of 2, so it's second order. Okay, then the last piece of this puzzle is half-lives. So in AP Chem, we are going to ignore the half-life for a 0 order and for a second order. If a problem tells you that you have a half-life, that is a dead giveaway that you are first order. Like instantly in AP Chem, if it has a half-life, that is it's a cheat code. It's first order. In real life, that's not true, but in AP Chem, it is. So the half-life is equal to 0.693 over K. And come on, mathletes, do you recognize this number 0.693? Probably not. Okay, so
No.
what?
No.
No,
It's wrong. It's
Not-
wrong.
okay, so the definition of a half-life is the time for a concentration to drop in half. So the time for a concentration A to become 1/2 of A. That is your half-life. So like if I have a gallon of water and I slowly pour that gallon out, how much time does it take for it to get to half a gallon? That's called a half-life. And the weird thing is that for first order changes, the half-life is always constant, no matter what you start with. So let's say I have my gallon of water and I pour it out until I get half a gallon, and that takes exactly 10 seconds to go from a full gallon to a half a gallon. If that pouring is first order, then for me to get from a half a gallon to a quarter of a gallon, because a half and a quarter are related, they're a half, like there's 2 quarters and a half, right? That will also be 10 seconds. That will also be 10 seconds. What about to go from a quarter to an eighth? I've cut my quarter in half. That will
10
take
seconds.
10 seconds.
But the rate's the same.
Because no, what's happening to your rate?
Staying the same.
No, because remember, if we drew out the rate graph, it curved. Right? It was a crazy.
Oh, are you talking about the first order or the?
No, for first order.
Oh, okay. I thought you were talking about the 0th order.
So even though you are like, we go from 1 gallon down to half a gallon, that's a lot of distance to cover or a lot of volume to pour out. Like we are doing it really fast. When we get down from a quarter to or a half to a quarter, that's less volume to pour out, but you're also doing it slower.
Got it.
Okay, so half-life is the time it takes for your concentration to drop in half. So let me scroll up here a second. Oops, I can't scroll up. Shoot, so we're going to clear out some stuff then. So I'm going to bring this equation down, and we're going to write it out. So give me an initial concentration. I don't care, any number.
500.
500. Okay, so the equation is that the natural log of some concentration is equal to the natural log of your beginning concentration. And you said natural log of 500 minus K times T. And that's going to be equal to, I need to drop your 500 in half. Okay, because it's a half-life, and you said our beginning was 500. So I need to get to half of 500. So I need to take the natural log of 250. Okay, so how do I get K and T by themselves?
Wait, is that why like the half-life thing, the 0.6393, that's ln of 2? So like when you minus them, like you divide it?
Exactly. Yes, good mathlete work there. Yes. So because we are always going to cut these in half, I don't care what number you gave me, Zafir. It could have been 2 billion and 1 billion. Like eventually I'm going to get to this natural log of 2. And so what we're going to get is 0.9693 equals K times T. And so if I solve for T, I'm going to get 0.693 over K. So really that half-life equation is this equation. It's just that you specifically have to choose A, 1/2 of A, whatever they are, and then solve for T. Now, the nice thing is they give you this equation on your equation sheet. So you really don't have to know what I just told you. You can plug it in. But that's it. Now, very, very last thing, units. Usually in chem, the units don't matter. But in this concept, in kinetics, they are always going to ask you for the unit because the unit is different in every single question. And you actually have to solve for your unit. It's a separate problem. And since we're running out of time, I'm not going to do that in this video, but I guarantee you there will be a what is the unit for your answer? Like that's going to be a question because it is a separate problem that you have to solve all on its own. All right, let's stop sharing.